So regular expression actually describes a language, right? So one natural question that comes up is, right, what are the class of languages? That can be described using regular expressions. Can we describe any language using this, or is there some kind of restriction, right? So regular expression is basically we have some building blocks and then you combine them using regular operations. So the name itself indicates why did we call them regular expression, right? If it is, it will be quite confusing if the class of languages that can be described using regular expressions is something and we have a separate class of regular languages. Thankfully, we don't have this confusion, because the class of languages that can be described using regular expressions is the same, which is the class of regular languages. That is what we have next to show. The class of languages that can be described using regular expressions is exactly the class of regular languages. So, right. So now we already saw two different ways to characterize or define regular languages, right? So these are the languages that can be recognized by a deterministic finite automaton, DFA. We also later saw that the class of languages that can be recognized using NFAs is the same. Now we have the third characterization, the class of languages that can be described using a regular expression, right? So three different characterizations. So now let us try to see how to show this, right? So the theorem is that a language is regular if and only if it can be described using some regular expression. So IFF denotes the if and only if, right? So sometimes it's a commonly used abbreviation, meaning a language is regular if some regular expression describes it. So something is described using a regular expression, that has to be regular. And then if a language is regular, then there has to be a regular expression that describing it, right? So both directions of the proof. So we prove it using two parts. One is the if part and one is the only if part. So if part meaning if there is a regular expression, the language described by that is regular, right? So in this particular in this lecture, we'll first show the if part, right? So if there is a regular expression, the language described by this regular expression is regular, meaning it can be. So as of now we have not proved the equivalence. We have not proved that. We are still in the process of proving that the class of languages is described by the regular expression is regular. So now we have to show that there is a DFA for this or there is an NFA for this, right? So what we will do is, let's say there is a regular expression. It describes some language. Let's say R is a regular expression, right? It describes some language LR. We will show how to construct an NFA for this, right? So what we do here is we describe a procedure to construct an NFA, right? So we will not give the NFA itself, because then it depends on the expression, right? So depending on what the expression contains, we will explain how to build the corresponding depending on what the regular expression contains, we will show how to build the NFA, right? So if you remember the regular expression, the definition had 6 things. It could be a symbol, it could be an empty string, it could be empty set, or it could be a combination of these using regular operations, union, concatenation, or star. So let's see, for each of these we explained how to build an NFA. So suppose the regular expression is just consisting of a symbol, right? Of a symbol, let's say A. So now let's we already know how to construct an NFA for this. We can have a start state and we can have an accept state, and that's it. This simple NFA accepts only the string A. There is nothing else that it accepts. You can verify this. Suppose R is the empty string, right, which means that NFA can only act, like we need an NFA that accepts only the empty string and nothing else. That's also easy to construct. We can construct an NFA like this, which contains only one state, and the start state is an accept state. So the empty string will be accepted because the start state is an accept state. If there is any more symbol, right, this machine cannot process it because there is no arrows outgoing, right. So if the string 1 or 0 1 0 is input, we don't know, we cannot process the string because there is no outgoing arrows from here, right. So this accepts only the empty string. This is a valid NFA that only accepts the empty string. Now if you want to consider the regular expression empty set, that's also easy. We can have a one state NFA again, which just has a starting state and with no accept states. So there is no accept state, so then nothing is going to get accepted. In other words, it accepts only the empty set, right. So because nothing is going to get accepted. So there you go, three simple NFAs that accept the language, just the symbol A, just the empty string and nothing. And then we have given R1 and R2 being regular expression, we have the union, concatenation and star. So what do we do for this? The solution is the same for all of this. We have already seen that regular languages are closed under union, concatenation and star, right. So we can rely on the same thing here. So suppose I am giving you a regular expression R, which is of the form R1 union R2. Now we by induction we can assume that R1 is a regular language and R2 is a regular language. Now since we know that R1 regular languages are closed under union, it follows that R1 union R2 is also regular. And similarly for the concatenation, if R1 is regular and R2 is regular, then the concatenation also is regular. We have already seen that in the previous lectures. So by induction it follows that R1 concatenation R2 is regular, and similarly it follows that R1 star is also regular. So therefore whichever way we describe the regular expression, be it a sigma or a epsilon or empty set, and if it is built using the regular operations, in whatever may be the case, we can say that the language is regular. So this is a very kind of a constructive proof, but just to get a feel of this, perhaps we can do a example, right. So the example is, let's take 0 1 star union 1, right. So let's see how to build this, right. So let's first consider 0. So this is an NFA that accepts only 0. Similarly, there is an NFA that accepts only, this is an NFA that accepts only 0, and this is an NFA that accepts only 1. And from this we need 0 1 star, right. So if you recall this, the proof for showing that the star operation, regular languages are closed under star operation, involved something like this. So we want to build the NFA for 1 star. So this is the NFA for 1. Now 1 star, we need to make an epsilon transition from the accept state to the start state, but this does not accept the empty string. So for that we need a new start state which is also an accept state, and then have an epsilon transition to the older start state. All right, maybe I'll just, there's a bit of right. So this accepts 0. So maybe I'll just draw this. This accepts 0. This accepts 1. And this accepts 1 star. Now, how do we get a machine that accepts 0, 1 star? So we can basically, what we need is, so let me just copy paste this. This may be easy. Right. So let us keep it here. So this is, so basically 0 concatenated with 1 star. So this is 1 star, and basically we need to combine the we need to have an epsilon transition from the 0 machine to the 1 star machine. So maybe what I'll do is I'll redraw the 0 machine. This is the 0 machine. The second state, which is this state, would have been an accepting state for the 0, but now that we are concatenating, that is no longer the case. So it will be like this. So this accepts 0, 1 star, right? And I need union with 1. So maybe I'll just replicate the 1 machine here. Right, so now the machine on the top, this accepts 0, 1 star, and this accepts this accepts 1. We need the union of this. Again, we can construct using the closure properties that we saw earlier, right? So the way to construct the union is you have a new start state, and then you have epsilon transitions to the two machines that accept the respective languages. So now this combined machine, right? So maybe I'll just right, with all the listed things. I'll just maybe pull it down a bit. So this accepts 0, 1 star union 1. Accepts or recognizes this regular expression. So this is how, if we are given a regular expression, how to construct an NFA for it. Right. So this is, so we saw the proof, which is an abstract, and then we saw an example where we build an actual NFA for a specific regular expression. Right. So there are other examples that are worked out in the book. So when I say book, I mean of Sipser. So I'm just restating the examples in case you don't have the Sipser, but you want to work out. So one is AB union A star, the other one is A union B, the whole star, followed by ABA. You may want to work that out. And that's all that I have in this particular lecture, but I'll just summarize everything. So we saw what are regular expressions. This is another way to describe languages. So basically it is like A epsilon and empty set, and then combined using regular operations. Then we said that we saw examples, and then we said that the class of languages represented by regular expressions are the same as regular languages. And then we said that the proof has two directions. Anything that can be expressed using a regular expression is regular, and we gave a constructive proof for that. Anything, so we explained how to construct an NFA given a regular expression, how to construct an NFA that recognizes the same language. So we also worked out an example for a simple regular expression 0 1 star union 1. And what we have not done is the other direction of the proof, the only if direction of the proof. So this will require us to show that if I give you a regular language, meaning if I give you a language that has a DFA or an NFA, right? So something that we know is regular as per our previous definitions, then we want to build a regular expression that describes it. So given a DFA or given an NFA, it recognizes some language. Now we have to build a regular expression that describes it, right? Because all we have shown is that anything that can be described in a regular expression is regular, meaning for all you know at this point, regular expressions describe only a subset of regular languages, but we want to show that it actually describes everything. Then we have to show the opposite also. You take a regular language, perhaps a DFA or an NFA, then construct a regular expression for that language. Right? So that is what is pending. This will be shown in the next lecture.